All right, so we're going to go ahead and continue our discussion with humidity, evaporation, and boiling. So relative humidity is going to be defined as how much water vapor is in the air compared to the maximum saturation possible. Okay. Then we have the dew point, which is the temperature where relative humidity is 100%, and fog may result in condensation of water droplets if they are small enough to stay in suspension. Okay. We have this idea of relative humidity, and we are able to calculate the percentage of relative humidity by the vapor density divided by the saturation vapor density times 100%. Okay, so let's look at this image here. In A, we don't have a top here. Okay, that's the main difference between these two. Okay. There are molecules, water molecules around here, and they are, they have some velocity, okay? And because of their speeds, their velocity, and kinetic energies, some of these molecules can break away, okay, from their liquid phase here, and go into their vapor phase. And that's they're able to do that even if they are at a temperature below the ordinary boiling point. Okay. Now, if we have the same kind of container with a lid here, so if it's sealed, we will have that same evaporation. Okay, so that's what we're calling this water to gas phase or vapor phase. It's going to be our evaporation. And with this sealed top, it's going to continue until there is so much vapor density such that the condensation rate to equal, the condensation rate will equal the evaporation rate. Okay, so remember, so evaporation is going to be from our liquid to gas. Okay, now our condensation is going to be the opposite. It's going to be gas to liquid. And maybe you guys have heard about this when talking about the water cycle. Okay, so this is that same idea. Okay, now let's look at an example, and then I'm not too worried about these last few slides for you to understand them, but just kind of giving you guys some more information. And then I'm going to look at a PhET simulation here in a minute. Okay, so let's quickly look at this example. Example 13.12. It states that this table 13.5 gives the vapor pressure of water at 20 degrees Celsius as 2.33 times 10 to the third pascals. Use the ideal gas law to calculate the density of water vapor in grams per meters cubed. That would create a partial pressure equal to this vapor pressure. Compare the result with the saturation vapor density given in the table. Note molecular mass of water is 18 grams per mole. Okay, so let's start with the idea of what density is. Remember that density is a mass divided by a volume. Okay, and so when we're looking at the ideal gas law, PV equals nRT. Okay, we know R, we know the temperature, we know the pressure, but we don't know the number of moles, but that's okay. Okay, so what we're going to do is instead solve for V over N. Okay, And then when we're looking at our mass, we're just going to use this here. So our mass, we're not going to divide by Avogadro's number like we have in the past. We're just going to use this here, 18 grams per mole, okay? And again, that's because when we solve for our volume over N, it is going to be in meters cubed per mole. That will be our units for this. Okay, so this is what we're going to do. So let's solve for V over N. That's going to be R times T divided by P. Okay, so V over N is going to be equal to 8.31 joules per mole times K. Then we have our temperature. Whoops, sorry about that. Our temperature is 20 degrees Celsius, which is going to be 293 Kelvin. Okay, and we're going to divide it by our pressure, 2.33 times 10 to the third pascals. Okay, so from this, we get an answer of 1.04 meters cubed per mole. Okay, now what we're going to do is we're going to take our density and plug these values in. So our mass is 18.0 grams per mole. Our volume then, or V over N, is going to be 1.04 meters cubed divided by mole. Okay, our moles will cancel. We'll get an answer in grams per meter cubed, which is good. That's what we wanted. And plugging this into our calculator, we get 17.2 grams per meter cubed. So this is our density of the water vapor. Okay. All right. So moving on, I wanted to get to this. Let me turn off my pen. And we're going to go to this simulation, and I just kind of wanted to show you what we're kind of looking at in terms of states and so forth. So this is actually going to be on your lab, but I wanted to give you guys a little bit of a rundown of this thing. So what I did is I pressed states, okay, and that'll be your first step in your lab as well. And I'm just going to kind of start exploring. So we learned a few major things. Okay, so the first thing I wanted to show you is if we start with some substance, and this is a solid, okay, and we cool it down, okay, you see how the ice cubes come out? We keep cooling it. Okay. Doesn't want to cool down more than that. Okay, there we go. So here's our temperature up here. See how it says 0 Kelvin? So this is at absolute 0, which is, we can't really reach that in the real world, but this is the idea, that the molecules will completely stop moving. And that's what we have here exactly in this solid. Okay. We have cooled it so much that the molecules are no longer moving. Now notice when I start heating it up, the molecules start moving again, okay? And they're just barely moving, they're kind of vibrating back and forth, okay? But that's the idea of a solid, okay? Now, I can make these molecules now into a liquid, and you notice they're moving a lot more and they're more fluid-like, okay? They're kind of freely moving about. And you see even one just became a gas, okay? I can click on gas, and now you notice that the atoms are moving a lot more. They're bumping into each other, and they just keep moving around, okay? So you're going to kind of explore this in your lab and kind of play with what happens when you maybe cool the system down or when you heat it up. Just kind of observing a few things, what happens, okay? That's going to be with a lot of your looking at different atoms and molecules. So now I'm looking at water, and I'm going to heat that up. And you notice they're moving a lot more. You've even got some that are spinning. Now finally, some of them are becoming gas. Okay? All right. You can also look at this next section. These are phase changes, and I'm going to kind of show you a little bit around this. First of all, we are not worried about this interaction potential, so we're going to go ahead and put that away. So just like this last one, you can heat and cool the atoms. You can pump more atoms in. Okay. You can increase or decrease the pressure. So we've got this container and we can increase the pressure. Okay. And you're just wanting to kind of see what happens when you do these different things. Okay. Again, changing the atom or molecule. And we also have a phase diagram here, and you will be drawing this in your lab as well, or labeling. So you just want to make sure that you understand what's going on here, what happens when you do something to the pressure or so forth. Okay? All right, so that's all I really wanted to show you on that. And that is the end of our lecture. So I'll go ahead and get these up. I'll get the lab up and the homework, and we will go from there. Hope you have a good week.